So if a company sends monthly shipments to its warehouses in several cities, how might they keep track of the shipments to each of the warehouse most efficiently? Matrices come to play in an application like that. So for example, here's a furniture shipping warehouse. The Easy Life Company manufactures sofas and armchairs and 3 models, A, B, and C, and the company has regional warehouses in New York, Chicago, and San Francisco. And in its August shipment, the company sends 10 Model A's and 12 Model B's and 5 Model C sofas, and 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each of its warehouses. So we would use a matrix to organize that information. So with the understanding that the numbers in each row refer to the type of furniture, sofas and chairs, and the numbers in the columns refer to the model of those sofas and chairs, then that matrix would look like row 1 is 10, 12, 5, and row 2 is 15, 20, and 8. Okay? So for example, this is 10 Model A sofas, and this is 15 Model A chairs. So the first thing we want to talk about is matrix size. And your examples are a little bit small, but hopefully I left you enough room to write in your dimensions. The matrix that is given there is a 3 by 2 matrix, 3 rows, 2 columns. Matrix B is a 3 by 3 matrix, which we'll also note a little bit further along, is called a square matrix. When your rows is equal to your columns, it's called a square matrix. And then matrix C is a 1 by 5 because it's 1 row with 5 entries. And matrix D is a 4 by 1 matrix because there are 4 rows but only 1 column. Now further on along in the notes, after we've talked about matrix equality, I'm going to point out to you now that this is a square matrix. This is called a row matrix because there's only 1 row, and it's also sometimes referred to as a row vector. And this is called a column matrix, which is also sometimes referred to as a column vector. The vector notation is used more in physics than it is in business. But in physics, vectors actually have direction. And those numbers mean something in physics as far as what the vector is measuring. So for example, in matrix size, as I said before, a matrix with the same number of rows as columns is called square. That would have been matrix B. And a matrix with only 1 row is a row matrix, and a matrix with only 1 column is called a column matrix, and they're also again called vectors. 2 matrices are equal only if they meet both of these conditions. If they are the same size, that is the same number of rows and the same number of columns, and if every single element in the first matrix matches up in position to every single element in the second matrix. So what that means is that if we have the matrix in part A there, 2, 1, Q, P, Q, and then X, Y, negative 1, 0, that's only going to be truly an equality if X has the value of 2, Y has the value of 1, and P is negative 1, and Q is 0. So those elements have to be identical for them to be equal. The statement that the matrix XY, which is 2 by 1, is equal to 1, negative 3, 0 can't ever be true because there are not enough elements in a 2 by 1 matrix to match up with the 3 by 1 column. There's too many entries in the column. We don't know what X and Y are. We would need 3 entries, X, Y, and Z. And hopefully some of this is fairly obvious just by looking at it. The matrix that we talked about in example 1, which was about the furniture, as I said, the 10 represented the August shipment from Easy Life Plant to each of its warehouses. And if matrix N gives the September shipment, what's the total shipment of each item to New York warehouse for 2 months? Well, in matrix M, we have the value 10. So this is 10 Model A sofas added to, in the other warehouse, 45 Model A sofas would give us 55 Model A sofas in matrix Q, and matrix Q represents the total shipment for both months. So what we've done basically is we're going to add matrix M to matrix N. And the way that you do that is you add the corresponding entries. 10 plus 45 is 55. And then 12 plus 35 is 47. And 5 plus 20 is 25. And 15 plus 65 is 80. 20 plus 40 is 60. And 8 plus 35 is 43. So we have the corresponding, this matrix, the sum matrix, which is Q, gives us the matrix for all of the shipments from the 2 warehouses. Or I'm sorry, for the 3 warehouses, all of the shipments for the 2 months from the 3 warehouses, okay? And if you wanted to know what all the shipments were for the first quarter of the year, then you would add up the 3 months matrices for those quarters. So this is a very realistic application of matrices. Now I'm going to pause here for a second and point out to you that yes, we did that by hand, but because we have this handy dandy matrix button on our calculator, we can go to matrix, go over to edit, and we could use M, N, and Q, but we'll use A, B, and C. So matrix A is going to be 3 by 2. This is a good place to review how you enter matrices. And the entries in matrix A, or we could have used M, are going to be 10, 12, 5, sorry, I put my teacher messed up. It's supposed to be 2 rows, sorry, and 3 columns. Shouldn't click and talk at the same time. So it's going to be 10, 12, 5 for row 1, and 15, 20, and 8 for row 2. And then we'll quit because you can't do anything once you've edited the matrix. You better go on out to the home screen before you go any further. Go back to matrix, choose matrix B, and edit it, and I'll get it done sooner or later. And it's also 2 rows and 3 columns, and its entries are 45, 35, 20, 65, 40, and 35. And then we will, just to be sure that we've actually entered the matrices correctly, we'll go and print out matrix A, make sure that it looks like it's supposed to. And then matrix B, make sure it looks like it's supposed to. And then in order to make sure we don't make any arithmetic mistakes, as long as we've entered the matrices correctly, we can enter matrix A plus matrix B and it will go ahead and print out the entries for the sum of the two matrices. So you don't even need a third matrix to do that. Now, if you plan on using that sum on the other hand, then you probably would want to do matrix A plus matrix B, and then try hitting your store key, because we might want to store it, and then we can choose a location for it, but we have to be careful that we choose one that's empty. We don't want to overwrite A or B. We don't want to use it to store over top of the ones that we're using. So now if you go back and you look on your matrix key, you'll see that you also have a matrix C, which is 2 by 3, and it happens to be the sum of matrix A and B. So if for some reason you wanted to hang on to that sum, you don't have to just see it on your calculator screen and copy it down. You can hang on to it and use it for something else. Everybody good so far?
No, for some reason,
Are you stuck?
no, I'm having a problem with it coming up. It's coming up with decimals instead of the right, my numbers are right in there, so I don't know.
That won't work.
Yeah, it's doing it again.
Is it like always?
I don't know what it's doing. I went back and checked those.
Oh, you're doing row ref.
Oh, what am I supposed to do?
Just printing out the matrix and then adding the matrix. So just go to matrix. And then choose A and print and hit enter. You just want to see it. And then matrix B. And hit enter, and you just want to see it. And if you want to add A and B, then you do matrix, choose A, plus matrix, choose B. Hit enter, it will actually show you the sum. And if you wanted to store it in matrix C, then you just hit your store button and then matrix and choose C. Even though matrix C doesn't even have any dimensions until you actually store something there, it will actually automatically adjust it for you. Okay? So, we have the September shipments from Easy Life Company to New York, San Francisco, and Chicago warehouses are given in the matrices N, S, and C for New York, San Francisco, and Chicago. What was the total amount shipped to the three warehouses in September? And the way that we would do that is simply add matrix N plus matrix S plus matrix C. And here again, you can enter it into your calculator and do that. I chose to put my matrices in A, B, and C. So matrix A is the New York warehouse, and it's going to be 45, 35, 20, 65, 40, and 35. And then matrix B is going to be also 2 by 3, and this is the matrix for San Francisco. 30, 32, 28, 43, 47, 30, and then quit once more, matrix, and edit matrix C, which is also 2 by 3, and it will have the entries 22, 25, 38, 31, 34, and 35. And then assuming that we've entered them all correctly, then we should be able just to say matrix A plus matrix B plus matrix C, enter, and we will come up with the same exact sum that we would if we had done this by hand. Okay? And then a question I might ask you on the quiz, once I have you come up with the sum, will be to tell me what is the significance of the 86. What does that mean? And what it means is that there's 86 Model C sofas that are shipped to the 3 warehouses in September. Okay? So you ought to be able to interpret what every number in that last matrix means, because that's an application. That actually is what they're good for. Any questions so far? Okay, now the next question is, or the next example says, find each sum if possible. Can you find the sum of matrix A plus matrix B for part A? Can you add a 2 by 4 to a 2 by 3? No. In order to add two matrices together, their rows and columns must be identical. So for matrix A, that isn't possible. Matrix B is a 2 by 3 and a 2 by 3. So can you add a 2 by 3 to a 2 by 3? The answer is yes. So you should be able to find that sum. So that should be the sum. Okay? Now, if you had tried to actually add those first two, if you had loaded that 3 by 4 into matrix A and then tried to add it to matrix B, what the calculator would have done would have given you an error message. It would have told you, I can't do that. Doesn't work. It would probably tell you something about a dimension mismatch. And that's because the dimensions of A and the dimensions of B do not match. So here we have another example, and this is our last example.
Can I ask one question real quick?
Sure.
Is there a way to clear out the matrix like that A, B, and C?
You can, but there's really no need to.
Okay, this is just too
Because
big.
every time you go in to edit it, you're going to change its dimensions, and it's going to automatically size itself and then change the value. So until you really need to put different entries in it, you don't have to. You don't have to ever set them back to being blank.
No, I meant like, where you hit second matrix and it has like A, B, and C and the two, like just taking that out.
No.
It won't, okay.
No. I mean, they're always there. They're part of the memory of the calculator.
Okay.
And then once you set up elements in it, it automatically gives you dimensions for those, but you can always change those dimensions. It comes in automatically set up that they're all 1 by 1. 1 row, 1 column, 1 entry. So during September, the Chicago warehouse of the Easy Life Company shipped out the following numbers of each model. 5 Model A sofas, 10 Model B sofas, 8 Model C sofas, 11 Model A chairs, 14 Model B chairs, and 15 Model C chairs. What was the Chicago warehouse inventory on October 1, taking into account only the number of items received and sent out during the month? And in order to complete the problem, we're going to have to go back up to the Chicago problem and see that we started out with Chicago having shipments in September of 22, 25, 38, 31, 34, and 35. So that's those shipments. Let's go put that matrix in. And actually this time we'll actually put it in matrix C so we'll know we're talking about Chicago. So here's Chicago shipments. And it is 2 by 3 still. 22, 25, 38. 31, 34, 35. And then this is what their September shipments were. So then we'll go and we'll put that in another matrix. And we could put it in A or B, and we don't have a matrix K. So we just go to any one that's empty and just remember which one we used. And again, it's a 2 by 3. And we have 5, 10, and 8, and 11, and 14, and 15. So this is basically what we have in matrix C was what was in September, and what's in this matrix, matrix D, is what's going to be shipped out. So what we want to do to answer the question is we want to take what was actually in the warehouse at the beginning, which is matrix C. Oops, and we don't want to do that. And we want to take out matrix D, which is the amount that was shipped out. And that'll tell us what's in the warehouse as of October the 1st. Now in reality, probably most companies do these matrices on a computer program. They have them actually programmed in and stored. So they do it with a database and they query the database, but this is what the database actually does, is it adds and subtracts matrices, or what it calls arrays. An array and a matrix is the same thing. So there is a way to automate it beyond what we're doing. You can also multiply matrices. If you can add them and subtract them, you should be able to do other math like multiply them. So that's what we're going to look at next. First thing we're going to look at is what's called a scalar. And in this case, what we might have is we've got a shoe store that has two particular kinds of shoes that they sell mostly at the holiday time, 2 kinds of slippers. And they have 2 different stores, maybe. So in store number 1, they have 3 of the first model of shoe. And in store number 2, they have 4 of the second model of shoe, or the first model of shoe. And then the second model of shoe isn't carried in store number 1, and they actually have 1 on order. That would be the interpretation of a -1. They've got 1 on order right now. Now, suppose Christmas is coming up and they know that during Christmas they sell more, like 5 times more than they usually sell of anything. So they might want to scale their inventory up to meet the sales in Christmas. Or for this particular one, since this is not an application, this is just a, how do you multiply matrices, then what you do basically when you multiply matrices is you multiply the scalar times each entry in the matrix. So -5 times 3 would give us -15, and -5 times 4 would give us -20, Negative 5 times 0 is going to leave that as a 0, and negative 5 times negative 1 becomes positive 5. And again, you can do that on a calculator. You would just enter in your matrix and then put your scalar in it. So for example, with the matrix we already have in the calculator, let's talk about matrix C. Matrix C is what was in the warehouse in Chicago on the 1st of September. If we want to know what it would look like to double matrix C's inventory by the 1st of October, then what we could do is we could take 2 and multiply it times matrix C. And that would double what's in the warehouse on the September inventory. So if we want to just double what's in on the 1st of September and have that in on the 1st of October if we haven't shipped anything out, then we can scale it however we want to by multiplying by a constant. The place where that's useful is when we actually find the product of two matrices. So if you want to understand the reasoning behind matrix multiplication, let's look at Easy Life Furniture Company again. Suppose sofas and chairs of the same model are sold as sets. Okay, you have sets of sofas. So W shows the number of sets of each model in each warehouse. So New York has 10 sofas and chair pairs of Model A and 7 of Model B and 3 of Model C. Chicago has 5, 9, and 6 respectively. San Francisco has 4, 8, and 12. They'd like to know what the value is of their inventory. And what they know is that the value of the Model A set is $1,000, Model B is $1,200, and Model C is $1,400. So if they want to know the value of their inventory, what they want to do is they want to multiply the first row by 1,000, the second row by 1,200, and the third row by 1,400. But that's only for New York. And then they would have to do the same thing for the other warehouses. So we could actually do that more efficiently if we had a scalar model, which would be 1,000 for Model A, 1,000 Model A, 1,200 Model B, and 1,400 for Model C. So that would be doing this like this. And we could do all we did on this previous page with a pair of matrices that we find the sum of. So what we're first going to do, I'm going to go back to the first page and we're going to go back to the matrix W and we're going to enter it in the calculator. So I'm going to clear all this out. Matrix, choose matrix I. We're going to edit matrix A, and this is going to be a 3 by 3 for the 3 warehouses and the 3 sets, the 3 kinds of sets. So 3 warehouses, 3 furniture sets, 3 styles. And there are 10, 7, and 3 in New York. There are 5, 9, and 6 in Chicago, and there are 4, 8, and 2 in San Francisco. So we have a matrix that tells us what is in each warehouse of each pair of sets. And a Model A set is $1,000, a Model B set is $1,200, and a Model C set is $1,400. How would we want to arrange to multiply this to be able to get these totals to replace that row? We would have to have a matrix that would multiply 1,000 times the 10, and 1200 times the 7, and 1400 times the 3. But we would also want it to do the same thing, multiply 1,000 times 5, 12,000 times 9, and 14,000 times, or 1,400 times 6, and the same thing with the last row. Well, we actually want to multiply something, okay? We have to think about how the matrix multiplication might work. Now, there's two different possibilities if you think about it. We've got to have a 3 by something or a something by 3. We've only got one set of values, and there's 3 in that set. So it's either going to be a 1 row with 3 values across the row, 3 columns, or it's going to be 1 column with 3 rows. Okay? We're going to try it both ways so that you can see which way works, because we know that it could be either one. So we're going to go in, we're going to go to Matrix, and over to Edit, and I'm going to choose Matrix B first. Now I'm going to try 1 row and 3 columns. So if this works, it should be 1,000, 1,200, and 1,400, if that's the way that it works. But then while I'm here, since I'm not sure which way this is going to work, and I think you learn something by playing around and thinking about how you might do it. Then I'm also going to go to Matrix C, and I'm going to make it a 3 row, 1 column, and put it in that way. So 1,000, 1,200, 1,400, and now I'm going to quit. Now Matrix A is in there exactly the way it's supposed to be. Here's what Matrix B looks like. And here's what Matrix C looks like. Those are called actually transposes of one another. When you swap out the rows and the columns, it's called a transpose. Now, if I want to multiply the matrices, I want to multiply I'll kind of tell you something that's going to come up in the presentation. Multiplication in arithmetic is commutative. You can switch 3 times 2 and 2 times 3, you still get 6, right? Matrix A times B does not equal matrix B times A, necessarily. It doesn't work that way with matrices. So what we're going to try to do is we want the scalar, which is the prices, to multiply times the inventory matrix. So the first thing we're going to try is we're going to try to multiply matrix B times matrix A and see if it does what we want. Did it? Because I get 21,600, 29,000, and 13,000. Does that even represent anything that we were looking at? In fact, do those numbers mean anything? No. Okay, let's try multiplying matrix C times A. Tells us there's a dimension mismatch. Oops. And if I tell it to go to, it just goes back to its system. Oh no.
I did A times C and not the answer.
Okay. So let's try that. Matrix A. Oops, let me better clear that off. It won't like that at all. Matrix A times matrix C. Does that answer mean anything?
Mine does. But yours is.
I think you had 100 instead of 1,000.
Okay, let me go check. And C,
Yes.
I could very well have. Yes, I do. Thank you.
We can get this out of math.
Okay. Does that tell us anything useful? Where do you see those numbers? That's the total value for what's in warehouse A and what's in warehouse, well, not A, the New York warehouse. The San Francisco warehouse is the bottom one, and the Chicago warehouse is the one in the center. Okay? So we did not have to individually multiply each row. There is a way to get the calculator to do it for you. But, remember I told you multiplication of matrices is not commutative. A times C did not give us the same thing as C times A, and in fact it told us C times A, it couldn't even do it. Okay? Now, when it gave us A times B, it gave us numbers that we couldn't even tell what they were good for. It didn't tell us anything useful. So what we wanted, since we were wanting total inventory, was we wanted to take all of the Model A's and multiply by 1,000, all of the Model B's multiply by 1,200, all the Model C's multiply by 1,400, and then add A, B, and C together. That's what matrix multiplication does. So here's a whole page of arithmetic that we could have done by hand, and there's a matrix multiplication we could have done a lot faster. So matrices are a much more efficient way of doing calculations that you normally would do with an array where you're trying to maintain your inventory control or order control or looking at some aspect of a lot of different products. You could also have taken the selling prices and this price that we just got by multiplying and looked at it this way, and that's actually what we just did by trial and error. We made up the price matrix, which they called P. We put it in a different matrix and multiplied it and got a matrix V by multiplying the original warehouse matrix by the price matrix and got the value matrix. They chose their letters for a reason, but we don't have those letters. So our example for a non-application, we'll just illustrate what we've learned by trial and error. The product AB of matrices, the way that you actually do this so that you know what the calculator is doing. Once you've figured this out, then you'll know which way you should have to multiply. When you multiply A times B, what you're doing is you're taking all of row 1 by all of column 1 in matrix B. So 2 times 1 and 3 times 8 and negative 1 times 6. And you're going to add all those together, and that's going to give you 20. Then you're going to do the same thing. 4 times 1 plus 2 times 8 plus 2 times 6 is going to give you the second row entry. And that's going to be 32. So the product of this 2 by 3 matrix and this 3 by 1 matrix is 20, 30. So it's a process of multiplying and adding. It's not just scalar. If you multiply a matrix by a single number, that's called scalar multiplication. You basically scale every entry. But if you multiply a matrix by a matrix, you're actually multiplying and adding some things. And for that reason, it's very important to realize that when you take a 2 by 3 times a 3 by 1, this is what has to match. The inner dimensions of your two matrices have to match. And then the resulting matrix is going to be defined by the outer dimensions. So if I had a 4 by 3 and a 3 by 5, my resulting matrix would be a 4 by 5. Okay? As long as your inner dimensions match. And it has to be for the order you put the matrices in. A 5 by 4 and a 1 by 5, you can't even do that, because the 5 and the 1 don't match. So you have to make sure your inner dimensions match. In other words, the number of columns of A has to be the same as the number of rows of B. So to find the product CD, we have a 3 by 2 and a 2 by 3 and a 3 by 2. And because the 3 columns of the first one and the 3 rows of the second one match, our result is going to be a 2 by 2, which seems strange because that doesn't look at all like either one of them, but that is the appropriate product. It's going to be -3 times 6 and 4 times 2 and 2 times 3 added together, and then 5 times 4 and 0 times 3 and 4 times -2 added together. We're going to have those dimensions, but it's much, much faster to do them on a calculator. Can I find the product DC? Why not? What is D? 3 by 2. And the other one's 2 by 3. So yes, you could. Would the resulting matrix be the same size? What would it be? 3 by 3 rather than 2 by 2. Okay? So you can turn them around, although not necessarily always. Just because C times D is defined doesn't mean D times C is defined. And even if it is defined, it's not necessarily going to be equal. Okay? So matrix multiplication is not commutative. And here's the example. There's the result of C times D, but then here's the result of D times C. Yes, you can reverse the two, but no, you do not get the same answer. Okay? Everybody good? So this is just a restatement of what I just told you. Matrix A and matrix B, if you line them up in the order you're going to multiply them, as long as the columns here match the rows there, then the resulting matrix is going to be this number of rows and this number of columns. But if you flip these two around and 4 and 2 don't match, and this time they sure don't, then the result isn't going to be a 2 by 2, the result's going to be not defined, because 4 does not match 2. Now, I'm going to let us take a little break at this point, because we actually can mostly finish tonight. We're going to talk about inverses, and the reason we're going to go ahead and talk about it, even though it's not exactly related to adding and multiplying, it is sort of related to multiplying, but it's going to give you another way to solve a system of equations that I think you might appreciate. Even though the row ref thing works really well, you can also use something called the inverse of a matrix to solve a system of equations. So let's take a little short break, give you a chance to stretch your legs, wake your brain up, go outside and get warm. I'm not
suffering with being cold in this class.
Yes, really. This class, that's the downside. This classroom is always cold, and so is the one next door. My office is cold today too, though, so that might have something to do with it. Actually, I'm gonna